working on time. And today he'll tell us about his work on CHIME, FRB Outriggers, and cosmological applications.
I'm going to click this. Got it.
Oh yeah, here.
Oh, that's you. Okay. Yeah, thanks, Leung, for having me here today. And I've met many members of the FRB group here, and it's been really great to talk to everyone about what they're doing. It's really exciting times, especially these 2 weeks in FRBs. But today I'm going to talk about a broader effort that we've been undertaking throughout time to localize a bunch of our FRBs. And independently, I'm going to talk also about application of FRBs in gravitational lensing and a new technique we've developed to search for lenses within FRB voltage data. So for those of you who aren't experts, I'm going to talk for a bit about what fast radio bursts are, give a brief overview of the Canadian hydrogen intensity mapping experiment, the instrument that we've been using to detect all these FRBs. I'm going to talk briefly about our efforts to localize FRBs over a wide field of view of sky with FRB Outriggers, which will give us 50 milliarcsecond localizations over 200 square degrees of sky, which corresponds to a rate of about 600 localizations a year when the whole array is up and running. And then I'm going to talk about something totally different, which doesn't depend on Outriggers, but which is a kind of a neat science program you can pursue in parallel, which is using the voltage data you collect for VLBI to search for compact objects, subsolar masses, and using the search to constrain the presence of primordial black holes floating out there in the IGM. So fast radio bursts, as their name implies, they are bright millisecond or briefer radio transients. And most of these things don't repeat. And the fact that they don't repeat and they are so brief means that they're very elusive. And even though they were discovered in 2007, we've pinpointed about 20 or 30 of these transients to their host galaxies, which makes them really difficult to study. They are extragalactic, meaning their luminosities are effectively unconstrained unless you measure their redshifts of their host galaxies. And we have strong reasons to think that they are associated with magnetars due to the efforts of the STARE-2 group here at Caltech, and also the detection of the exact same radio burst from a galactic magnetar, STR 1935, which then has spawned a bunch of other efforts in this area, GREX. There are 2 other experiments to look at the whole sky for these giant radio bursts, galactic magnetars, which is really, really cool that we're trying to look at building instruments just for FRBs now. We're no longer, commensal backends sitting on someone else's experiment, which is great. If you take the rates of FRBs, they're pretty frequent. And one other cool feature is that they are dispersed by cold plasma because space is in a vacuum and it's got an index of refraction, and that index of refraction depends on the local density of the local plasma frequency, which is proportional to the electron density. And so when you detect FRBs, you can see that at high frequencies, the pulse comes in first, and there is a delay as you go to lower and lower frequencies. And only after you undo this dispersive smearing or this skewness that you get a millisecond duration radio transient, as I promised. So ever since these things were discovered, people immediately realized that you could use these extragalactic dispersion measures for cosmology to probe gas directly in a way that's independent of temperature, up to 10 to the 9 Kelvin, and in a way that's independent of metallicity, because plasma frequency is dominated by electrons. So that suppresses the metallicity dependence by a factor of a couple of thousand, the proton to electron mass ratio. And it's also independent of temperature because it becomes dependent on temperature only when the electrons start to move relativistically. And if you convert the rest mass of the electron into a temperature, this gives you 5 times 10 to the 9 Kelvin. This is a really neat probe that complements things like Sunyaev-Zeldovich effect and X-ray Bremsstrahlung at probing gas in and around galaxies and in more diffuse structures as well. So this means FRBs have enormous potential as probes of cosmology, not just through the dispersion measures, but in other ways as well, such as gravitational lensing, which I will talk a little bit about later. We wanted to, so I hope this motivates why you want to detect a lot of these FRBs. One great instrument to do this, that was initially not designed to do this, is the Canadian hydrogen intensity mapping experiment, which Leung has a lot of familiarity with. This is a phased array beamforming interferometer, usually used to map out 21 centimeter signal at redshifts between Z equals 0.8 out to 2.5. And the reason this is chosen is because this matches the epoch of the transition between matter domination and dark energy domination. So this sets our frequency band to 400 to 800 megahertz, and it turns out this is a nice sweet spot in which FRBs can be detected. They're not scattered into oblivion. We have a huge data rate, which rises from our large field of view and our large sensitivity. Each of these, you can see that CHIME is made out of these four reflectors, each of which is about 100 meters long and contains 256 antennas, each of which has collects dual polarization data. So if you were to take data from CHIME and write it to disk, it would come in at a rate of about 1.6 terabytes per second. It's a significant fraction of the North American internet traffic. So of course, we don't save all this data. A lot of our work is in reducing it in real time and in developing observational strategies that allow us to mitigate this large data rate. Let's see, next slide. Here's an animation of our observing strategy in horizontal coordinates. So the illuminated circle shows the sky that you can view from the telescope in telescope-centric coordinates. So right in the middle of this plot is zenith, and it's our primary beam is about 2-3 degree wide strip that's about 100 degrees tall. So this gives us a barcode strip that scans the sky once per night. And this strategy has allowed us to detect FRBs at an unprecedented rate. So whereas 50 FRBs were detected until 2018, in a year of operation, we detected about 700. Recently dropped a catalog of 535 of these events. And this detection rate has been sustained over the past few years of operation, wildfires and natural disasters in British Columbia notwithstanding. So this is, so we're trying to now expand this program to achieve this golden combination of high detection rates, so large numbers of FRBs, and high angular resolution. However, there's a big hurdle that we have to overcome, which arises from CHIME's heritage as a 21 centimeter intensity mapping experiment. We do not need angular resolution with CHIME for its primary science goal. And this results in CHIME's angular resolution being on the order of an arc minute. And you can do a little bit better than that if you centrate your data. So for higher signal to noise events, you can maybe get down to a couple of arc seconds, but this is just for the brightest FRBs. So then you'll lose this going to large numbers. The only way to go to large numbers with CHIME is to build VLBI outriggers and to observe over a wide field of view, same as CHIME. And so to give you a sense for what this gets us, with arc minute resolution, you're sort of left asking, okay, we detected this FRB, but where is the host galaxy? And people have been developing methods to pin down the host galaxy, even with this coarse localization. And the way you do this is you look at the dispersion measure of the FRB, and then you set the maximum redshift from which you're bursting routine. So you can actually take most of the galaxies here and throw them out because they are definitely too far. But this still doesn't work for all FRBs, so you don't have large numbers anymore. If you had precise localizations, you might be able to do something like this. This is one FRB repeater that's been localized to this white dot here. Now, this is not a host galaxy. This is a globular cluster inside of AB1. So the scientific question that you can ask now becomes much more clean, which is what is the local environment surrounding the FRB? What's happening in the neighboring 60 parsecs, 1 kiloparsec around the FRB? And this kind of analysis, I believe, is the key to uncovering the progenitors of FRBs at a population level, not just for single sources, such as this exceptionally strange FRB in a globular cluster, The localization here is actually so precise that you can look at how far from the center of the globular cluster is in optical light. Although it's not super clear what that gets you at this stage, the theorists are still catching up with this. So I hope this motivates the major challenge that we're facing of delivering a high angular resolution over a wide field of view. The Astro 2020 Decadal Survey also recognizes this challenge and suggests as a solution, a wide field radio time domain survey with arc-second localization capabilities like CHIME, but with sufficiently precise positioning for multi-wavelength follow-up to enable detection and characterizing these FRBs. So we have a pretty compelling science case to build other telescopes to observe at the same time as CHIME. And I like this animation because it shows very succinctly how we're planning to do this. So we use CHIME as a great FRB discovery machine, and we set up these very simple outriggers on long baselines from CHIME. And in real time, CHIME can send triggers and trigger the dump of voltage data at each of these stations. And the voltage data gets stored in RAM, and that buys you, with a lot of money, about 30 seconds of baseband buffer. So that gives you 30 seconds to get your trigger over from CHIME to the other stations. We've actually built this array. I played a central role in commissioning the digital systems and phasing up one of these outriggers tone on the bottom right. And I also led the analysis of data coming out of this VLBI array. It has a field of view of about 10 square degrees. And this means that with these little dishes, which reduce the sensitivity of the array, we can detect an FRB every couple of months, although like operations are quite difficult, so we haven't managed to localize every single one of those. Here's the array. There's CHIME at the top left, ARO at the right, and tone at the bottom. I'll talk a little bit about each of these instruments in a second. So ARO there's a 10-meter dish there. It was built in the 1960s. It's pretty old, so they just park it at a declination, and they stare at one particular segment of the CHIME beam. And on this dish, we measured the first VLBI fringes on an FRB on a 3,000-kilometer baseline. And we measured a bunch of single pulses from the crab pulsar and did VLBI on those things to characterize our clocks, which is a necessary step in VLBI. Tomas and I wrote a paper about this, available on the archive, and is now in Astronomical Journal. At Green Bank, Pranav built the array in the foreground with his bare hands. It's an array of 8 6-meter dishes. It's on the analog side, it's a prototype for Hyrax and also for a cord. But on the digital side, I built the digital system there. It's sort of a CHIME style backend, which means it runs CHIME software, and it can receive dump triggers from CHIME in order to dump the baseband data to disk in order to do VLBI. And so Pranav is now postdoc at Yale working on 21-centimeter cosmology. Here's an FRB that we detected. It has a dispersion measure of about 500 parsecs per centimeter to the minus cubed. One neat trick that I like is to take the dispersion measure and divide by 1,000, and that gives you an upper limit on the redshift that this FRB comes from. So for those of you who aren't experts in the audience, this is a nice party trick. If you're ever at a party and someone asks you, what's the redshift corresponding to a dispersion measure of 1,000 FRB, you can say, oh, it's at most 0.1. It works great. So we want to do VLBI. This requires pretty intense calibration, and the single source that we use for calibration is the crab pulsar. So we don't just measure FRBs, we measure a lot of single pulses from the crab. These are giant pulses that are kilojanskis bright. I've shown 9 waterfall plots here. Each column corresponds to a different single pulse event. So this left column corresponds to a crab pulse, which we're going to call C1 here. The middle column corresponds to the FRB we detected, and the column on the right corresponds to another crab pulse, C2, which we detected slightly after the event. So C1 and C2, one before, one after FRB 2021-06-03A. And we're going to use a combination of these crab pulses and FRB to localize it. There's an active maser at ARO, an active passive maser at Green Bank, and at DLAO. And these masers are what you need in order to stabilize your clocks to do VLBI. One challenge that we had to overcome is being a commensal backend, is that we need the absolute timing of GPS and also the very stable relative timing of the maser at the same time. And so Juan and I developed a way to do this. We inject the second clock into the correlator and read it out at some cadence in order to use that when we're doing VLBI observations. But for most purposes, when you just care about the GPS clock, you can stick to that. So I hope this convinced you that we have sort of the ingredients for an FRB localization. Now I'm sort of going to sketch how our delay model works. If you were to look at the dynamic spectrum of an FRB, this is what you would see if you could dump all of this data. I'm plotting the sweep of the FRB as a function of frequency and time. You can see that it comes later at lower frequencies, as I promised. And if you were to measure this exact same FRB at an outrigger or some other station, you would see the exact same sweep, but delayed by some characteristic time. That time delay is a couple of milliseconds for the long baselines that we're considering, although of course it depends on the geometry of your station and where the burst is coming from. And it's this geometric delay that we really want to measure. So this is a totally adequate picture if you're working on short baselines, but it turns out that on long baselines, it's actually woefully inadequate. And the reason is because as the burst comes in over 10 seconds or so in the chime band, the Earth rotates. So the delay changes as a function of time, and therefore as a function of frequency as well. So in addition to this contribution from the delay rate of the Earth, there's also yet another contribution from the differential thickness of the ionosphere, which gives you a genuine frequency-dependent delay because of the index of refraction of plasma, as I mentioned very early on. So hopefully we can separate these contributions to their different frequency dependencies, and this is just sort of an indication of how big these effects are. So in conclusion, there's this bulk geometric delay on the order of milliseconds, and there is field rotation as a function of time because of the dispersive sweep, which can amount to about a couple of arc minutes. You don't compensate for it. And then there's also this differential slant ionosphere measurement, which can give you uncertain, systematic shifts on the order of tens of milliarcseconds. For those of you who image with the VLA or with traditional radio observations, you might wonder how we're covering the UV plane. We only have two baselines, and we're covering the UV plane with instantaneous bandwidth, not with Earth rotation, even though that effect is seen in our data, as I just mentioned. And using our octave of bandwidth eliminates 2 pi phase ambiguities that arise if you observe with narrower band receivers. Here is an equation for our delay model. As I mentioned, the time delay depends on the localization, which is what we actually want to measure. There is this other contribution, which depends on the space weather and the position of the sun, and that's spatially and temporally varying. So at the end of the day, there's sort of 4 parameters that go into this. There's an RA and a DEC, which goes into your localization, and there's 2 delta DMs. And the reason there are 2 is because we have 2 baselines. We're considering CHIME and each of this outrigger station independently, and we're not considering the baseline between the 2 outriggers. So we fit a 4-parameter model. This is sort of what the model looks like for one baseline. And you can see that if you change the delay in microseconds here, you can introduce a slope into the fringe, the function of frequency. And by adding 1 over f term, you can also introduce curvature. And so the goal here is simply to measure the curvature at the same time that you measure the slope. And by separating those 2 contributions, you can simultaneously measure the ionosphere and the location of the FRB, if we've properly compensated for things like clock delays and everything else. You do this for both our baselines, and this is what you get. This is real data. On the left, these 2 plots are the lag correlation functions of our data. You can see that the burst is detected with some small residual delay, with a signal to noise of 30, 35 on both baselines. So this is pretty promising. And if I take a Fourier transform of this gives us phases. The phases are what we use to, if you want to image, you can use the phase of the image, but we're just going to fit a model directly to it. And so here are our phases. You can see that each individual point is not great. It's got an uncertainty of maybe a radian, but we have 1,024 frequency channels, and this allows us to fit this model and both break these 2-pi phase degeneracies, and also to simultaneously measure the slope and the curvature of the fringe. Our 4-parameter model gives us a likelihood plot. This is what that looks like. The contour that you care about here is the one where there's RA on the deck. There's lots and lots of potential solutions here. This results from our particular geometry of the baselines and also the spectrum of the FRB. We've here imposed a weak prior on the ionosphere based on the fact that we don't see much curvature in the fringes, so we just plot them. So this is not super justified, but it does help to reduce the amount of time it takes for this sampler to converge on this solution. We think the solution is pretty robust. Here's a localization. It's on top of a host galaxy. The target is huge in this case. This galaxy is tens of arc seconds wide. So even if we were a bit wrong, we would still, we're pretty confident that this is our host galaxy. As I mentioned earlier, the party trick is to say that the galaxy is at a redshift of its dispersion measure divided by 1,000. But this is actually sort of not what we measured. Oh, by the way, we measured the distance from the center of light to be about 9 kiloparsecs. It's on the order of what you expect from previous observations with ASCAP. That sort of checks out. We've also characterized a host galaxy using prospector. This is something that's done by my undergrad, Savannah Carey, who's starting at Berkeley next year, and Mohit Bhardwaj, who is the actual expert here. We used archival data from 2MASS and WISE and also SDSS. This is an SDSS galaxy in order to pin down the SCFD and the star formation history of this galaxy. Here are sort of the optical properties. I mentioned earlier that the dispersion measure is 500, but the redshift is 0.177. This points to a dispersion measure excess. So where could that possibly come from? I'll talk about that in a bit. It's almost an edge-on galaxy. The burst comes to us through a 7-degree sightline with respect to its disk. The stellar mass of the galaxy is maybe 10 to 11 solar masses, sort of similar to Andromeda. And it has a pretty unremarkable star formation rate here. And as I mentioned, the projected offset is 9 kiloparsecs. It's about 1/2 light radius away from the center of light. So everything sort of checks out. The galactic latitude of this burst, it's high. I'll talk about it in a second. Yeah. The precision of our localization allows us to zoom in on the local star forming environment of the FRB. Here I've shown a couple of spectroscopic extractions, and you can see that one of the only places that you see star formation in the galaxy is right on top of the FRB, which is kind of cool. If you study this in more detail, we actually see star formation from the region between A and B, but no star formation between B and C. So this points to the presence of like a star forming arm or something over here, although I haven't shown it at this point. So I mentioned that there's a DM excess compared to what we would expect from this redshift. The DM budget looks like this. You know how many electrons are in the Milky Way and its halo. You can subtract that out to redshift of 0.17. You get this many electrons from the intergalactic medium. So you can subtract all these components from the total, which is 500. And this tells you that there are 257 units of electrons in the host galaxy. And it turns out that you take the mass of that galaxy and the inclination angle through which you're seeing the FRB, that's perfectly consistent with what you'd expect from an edge-on plane parallel disk, which predicts between 200 and 300 units of DM. So this is kind of a neat system where we have the properties dominated by the host galaxy, not by the FRB source itself, which might be doing something strange. So we can then analyze the radio properties of this and look at what that line of sight looks like, because we know it to be dominated by the host galaxy. And this is a nice way to visualize this. So there's 3 variables here. There's the dispersion measure, the rotation measure, and the scattering time scale. We've measured these all for the FRB. And we've also compared those measurements to measurements from galactic pulsars divided into 2 groups. The blue group is low latitude pulsars, and the orange group is high galactic latitude pulsars. So you can see that the properties of the FRB are much more similar to the blue group, which is totally consistent with what we've seen from the inclination angle of the galaxy. This points to a pretty nice story where you have an unremarkable FRB source sitting in the host galaxy, whose properties are, through this line of sight, are more or less consistent with what you'd expect for a Milky Way-like disk. The source is, totally consistent with being a magnetar. It's in the disk. You see it with this almost edge-on geometry. So this suggests it's not in a globular cluster all the way out in the halo, although of course you can't rule out that there's a globular cluster in the disk. We see star formation in the kiloparsec scale vicinity, which is consistent with other localized repeaters, although this is the first time this has been observed for a one-off FRB. The properties are dominated by the galaxy rather than the FRB host. And we tried to measure the disk height, thought about it for a while, decided it was pretty hard because of the uncertainty in the inclination angle of the galaxy. And the reason you might want to do this is because magnetars are basically completely confined to their host galactic disks. They're 30 parsecs above or below the disk, whereas you might, if you were looking at an older population, you might expect a larger disk offset. However, 3 degrees is still too much for us to constrain that very tightly. So it's basically consistent with a magnetar or a massive young progenitor. We have not seen repetition in this FRB. We've had 36 hours of exposure since 2018. Here are a bunch of other radio properties we measured. We just measured everything we can. It tells a pretty clean, consistent story. So this is arguably more of a distraction. I spent a lot of time with this because I spent a lot of my time building up the foundations and for this measurement. But really, this infrastructure is designed for CHIME Outriggers, which is our next experiment, which will localize hundreds, thousands of these FRBs to their host galaxies with similar levels of precision. We'll get there one day. We're going to build cylinders. This way, we will have a wide field of view and high sensitivity, so that we can localize a large fraction, 60–80% of CHIME's FRBs. And this shows the first outrigger, maybe 80 kilometers away in various stages of construction. You can see a digital team putting together server racks, the telescope reflector in the Canadian winter, and down here, the reflector in the summer, where everything looks kind of beautiful. We've started taking data here. Here is a transit from this telescope alone. We haven't looked at fringes from between CHIME and this FRB Outrigger, but this telescope alone, we're in the process of characterizing it. It looks pretty nominal. You see a nice big peak here where you expect SIG-A to be transiting. So here we've made a map as a function of declination while SIG-A is overhead. We see nothing else. This seems promising. So this outrigger, everything's sort of proceeded according to plan so far. We have 2 others coming along. Here is, I can't load that video, that's okay. Here is reflector at Green Bank. It's on the East Coast and not the West Coast. So you notice that the half pipe is tilted. This allows us to observe the same field of view as CHIME. It's a 30-degree tilt and designed to withstand quite a big wind load because we've essentially built a sail. The third outrigger, click along, looks like an empty field here, but the important part of this empty field is that it is cleared of grass, which means that construction is proceeding. Things have begun. We've done a geotech survey and are sort of in talks with the SETI Institute to use this site to build our third outrigger. So in conclusion, I spent a lot of time working on these other instruments, the CHIME Pathfinder, which I didn't really talk about. Also, this little dish at Algonquin, these 8 dishes at Tone. I commissioned them, did a VLBI localization. It's kind of tells a pretty boring story, but really this is just a Pathfinder for localizations with these 3 outriggers that are coming, which will allow us to tackle some of these science questions that are accessible with ARC second level localizations. You can make Hubble diagrams using the dispersion measure. You can measure the large scale structure of the dispersion measure as a function of space. You can probe things like, the turbulence in the IGM. Maybe search for strongly lensed FRBs with galaxies, in addition to other scientific applications which are available with arc-length level localization. And the whole point of these long baseline outriggers is to take us to milli-arcsecond level precision. We're not going to try to get better than 50 milli-arcseconds because that's matched to the seeing of the best optical facilities like Hubble and now JWST. And this will hopefully allow us to get a handle on progenitor theories and characterize the host environments of FRBs, and allow us to study the dynamic, the properties of the gas on small scales around FRBs. So that's sort of this half of my research program. Another nice application of FRBs, not in mapping out the gas everywhere, but in using them as backlights for gravitational lensing. And this is something I pursued in collaboration with Riff Cater at McGill. So he's also a really great person to talk to if you're interested in this sort of science. So in this situation, we're looking for FRBs which as backlights behind not galaxy clusters, but behind putative black holes or possibly stars that are low masses. And essentially, we're just going to do a lensing search. There are 4 ways of doing this. 4 signatures of gravitational lensing. One, gravitational lenses make multiple images. The images' shapes are distorted, and it causes the brightness of the background source to change over time because of relative motion. And the 4th signature of gravitational lensing is just that the 2 images have a relative delay with respect to each other. And this is a bit difficult to measure because it's usually a really small delay for massive lenses like galaxy clusters and galaxies. But with the time resolution that afforded from these millisecond, microsecond FRBs, you can maybe directly measure a double pulse. And this is exactly the science that I'm proposing to do. So we've seen these 3 signatures elsewhere in lensing of quasars, CMB lensing, also transiting stars in front of other stars in a local group. And all I'm going to do is I'm going to search for doubly pulsed FRBs. Not super complicated. At this moment, you might wonder why FRBs? Why not GRBs? Why not supernovas? You can do this with AGNs as well. Your favorite transient, you can look for a doubly imaged version of those in the time domain. Now, the reason you want to use FRBs is because they're, you can use GRBs. The slide shows that. Rachel Webster did this last year and claims to have detected a 10 to the 4 solar mass black hole. But from a lens GRB, that looks like it has two bursts. Now, the reason you might want to use FRBs is because FRBs are actually extremely common. They happen at similar rates as supernovae. They have similar redshift distributions. And with new experiments like DSA 2000 and HORD, we will go even deeper. And that turns out to make the lensing probability much, much better. FRBs are also compact, which implies a short variability timescale. And that short variability timescale maps into an expanded physics reach of this microlensing phishing campaign. So FRBs are sort of between microseconds and milliseconds in duration, and this corresponds to lens masses that are maybe between 10 to the -3 solar masses. And by going to shorter and shorter timescales, we can access more decades in mass space. With FRBs, you have phase information, which you don't have at most other wavelengths, except for gravitational waves. And this allows us to push our time resolution from maybe a millisecond to 100 nanoseconds better. And that directly translates into being able to access lighter and lighter masked lenses. In other words, I'm proposing to do something like the right, whereas on the left, we have the correlation of 2 light curves. You can look for the same structure in the light curve happening twice. But on the right, you can look for the exact same double image, but interferometrically, because you have voltage data and you're not relying on morphology arguments to say that you're looking at the same image, the same burst image twice rather than a double peak. And that gets you from 10 to the -6 second time resolution to maybe 10 to the -9 second time resolution. So what do we see? We developed a pipeline to autocorrelate our data coherently. Riff Cater and I worked on this for quite a long time, and we developed a formalism to search this delay spectrum for fluctuations that are statistically significant. So, for example, you might be interested in those fluctuations, or maybe even that one. but not all the ones that are sort of just blades of grass down here. We developed a statistic that we compute for each of these peaks to quantify how significant it is. That's the number of statistical fluctuations we expect per data set. And then we do this for 200 FRBs. So now we have a bunch of values of n, and we're looking for very small values of n, because small values of n signify that they are less likely to occur per data set. So if we see a very small value of n, then we might want, that might warrant further study. So we do this, we build up a large number of n values, and we do this for a bunch of FRBs. And here is a cumulative distribution of all the n values we have, this blue curve here. We of course are only interested in the high, in the tail of low n, because those events are statistically unlikely. That there are 59 such excursions, and of those 59, only 16 of those are consistent with having magnification ratios that are consistent between the two telescope polarizations. So of those 16 excursions, you can do this exact same analysis for off-pulse data. And there are similar numbers. So you can now, the next thing is you do a KS test to see whether the green curve here is similar to the green curve here. And the answer, unfortunately, is not quite. So you might say that, well, there is an outlier here. It's at 10 to the -7, 10 to the -8 false alarm probability. What does that look like? If we actually inspect this guy, well, there are peaks here, but there are no digital artifacts. You can see that there's a lot of structure in the autocorrelation function here. It turns out that that outlier corresponds to the edge of one of the, corresponds to the, it's an edge case where the outlier falls in a bin which is otherwise very, 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 very clean, and therefore it has magnified statistical significance. Whereas if you grouped this star with the data on the right-hand side here, it would not look very significant. So this is I sort of identified a foreground in our search, and this foreground turns out to be diffractive scintillation from the Milky Way. I have been exploring this with an undergrad. We measured the scintillation timescales for a couple of different FRBs. Jacob is very familiar with this work. And we see broadly that the autocorrelation, decorrelation bands, are broadly consistent, this is a log scale, with what you would expect from any 2001 predictions. Eve is now graduated. She's starting at Berkeley. She has started at Berkeley this year. So given all these, all these events that we've looked through, haven't found a lens, we can now attempt to translate our null search into an upper bound on the presence of primordial black holes. The way you do this is you look at all possible geometries. You can look for asymmetric geometries and also symmetric geometries, taking into account the fact that at low, that you're limited for small angular separations, you're limited by the time resolution of your instrument and also instrumental reflection. So you sum over all possible geometries, all possible lens masses, and you get a curve like this, which tells you the expected lensing rate as a function of lens mass. And what this curve tells us is that if there were primordial black holes of 10 to the -3 solar masses, we would either detect it or we can rule out that possibility because the optical depth is greater than 3 here. There would be 5 plus or minus square root of 5 of them along all of our sight lines combined, and we don't detect them. So then we can turn this upside down and turn that into a constraint. The main systematic here is in understanding decoherence along our line of sight. And the way this generally works is that we're setting up this big interferometer here where you have a source, a lens plane, and an observer plane, and the light takes both paths around the lens to the observer. However, if there was a scattering disk there, then you might decohere this interferometer. And this would be bad because there need not be a lens there, or there could be a lens there and you wouldn't see interference fringe. The way to think about this is to map your telescope here and instead think of it as 2 telescopes in the lens plane separated by a constrained radius. This takes you back from from this lensing experiment back into this radio interferometry experiment, where all you're doing is you're resolving a extended source over a huge baseline. So the Einstein radius is maybe a parsec or larger. So can you resolve out the scattering screen here? If this disk here, the scattering disk, looks like a point source, then you would still see the interference fringe. And if it looks too extended, then your constraints are worthless. It turns out that this depends on the scattering geometry. Your scattering disk looks bigger and bigger if your scattering screen is farther and farther away from the source. So if it's 100 parsecs away from the source, you don't have much sensitivity. And if it's really compact, if the FRB source, if FRB scattering screen is very close to the actual FRB, then your sensitivity is mostly untouched. You can see that there's sort of a low mass and a high mass cutoff for our constraints. On the low mass end, this arises from diffractive optics. So the light cutoff goes as the wavelength. So if you can go to smaller wavelengths or higher frequencies, you can push to lower and lower masses. On the upper end, this heavy cutoff, as you can see here, it depends on the scattering physics, which is also frequency dependent. But because scattering is worse at low frequencies, if you go to higher frequencies, you actually win as the wavelength squared in terms of how heavy you can go. In other words, the discovery space, if you take these two things and multiply some numbers together, the discovery space gets much much if you go to higher frequencies with experiments like CHORD and DSA 2000. It also goes with the square of the distance to the source because the lensing optical depth increases, which also increases your Einstein radius proportionally. So CHORD and DSA 2000 are definitely going to detect these lens FRB events, these microlens FRBs. These are interesting, not just because you might look at lens stars, but also because you might be able to use them to detect strong lens FRBs. Because generically, the microlensing happens in the macro image positions. So you might be able to find your galaxy lens FRBs by doing this microlensing search on a large scale with FRBs at high frequencies, which are coming to us from very far away. So in conclusion, we've done some early science in using FRBs to detect primordial black holes. Haven't found any. We've put some constraints on, and the constraints, I've argued, depend on the scattering geometry. If we think FRBs come from young pulsars, young magnetars, there is a lot of evidence for this, also some evidence against. But generically speaking, if you take a crowd pulsar as a rough proxy for what an FRB host environment looks like, then you can sort of say that, like, well, I'm going to assume that my screen is about a parsec away. And constraints, they look not so good compared to other constraints like from Ogle and from Eros. However, our constraints apply outside the nuclear halo in these long flight lines out to the IGM at redshifts of 0.2 to 0.3. And this is one of the only probes of primordial black holes at non-trivial redshifts besides supernova lensing. And it's also worth pointing out that this discovery space is really made possible by the fact that we're doing this coherent microlensing search strategy. If you didn't do that, you would be stuck at heavier objects, which supernova lensing already covers. This is a new parameter space we're observing with a new technique, which I'm really excited about, and which I think will be a real a key part of the science case in experiments going forward, which will look at FRBs at higher frequencies. So in conclusion, we're doing a bunch of stuff with the voltage data. I developed a coherent time delay search that can detect macho dark matter or rule it out. There's other applications in looking for stellar microlenses, as Leung will tell you about, or in sniffing out these elusive FRBs that are lensed by galaxies. We've studied the effect of scattering on this. It's okay. It will get better at higher frequencies, and we've identified foregrounds to this, being Milky Way scintillation. Zurif and I have published this in 2 papers in PRD, and even I have worked on scintillation in a note that she submitted to RNAAS. Meanwhile, I've commissioned a bunch of telescopes, the CHIME Pathfinder, which I didn't really talk about, but also the ARO 10-meter telescope, and also the TONE array. So those are 3 VLBI stations. Those are sort of deprecated now, out of commission. But I'm really excited for the next 3 VLBI stations, which will localize a large sample of FRBs to the host galaxy over a huge field of view. And so our test beds have retired many of the technical risks of this ambitious survey. We've localized an FRB Written a couple of papers with Tomas, with Juan, and my undergrad Savannah, who's now at Berkeley, localizing FRB, and keep an eye out for this paper. We're writing it up right now and doing some systematic cross checks. So at that point, I'd like to first and foremost thank all of our partners in the CHIME collaboration for their enabling this amazing science. I'd like to thank my hosts here at Caltech, Jacob and Liam, and for their hospitality and for great discussions about science. I'd like to thank all of you who are online watching this talk through Zoom. I know how hard that is. And now I'll take any questions that you might have. Thank you very much.
Thank you, Calvin. Okay, so just raise your hand on Zoom if you have a question, or raise your hand in real life. Wait, hold on. Go ahead, Casey.
Calvin, great talk, very impressive, and yeah, it's really fun to see all of the technical work and also all the great science that's already been demonstrated. So I was trying to get a little intuition because the lensing is kind of new to me, but so the upper mass limit cutoff you presented was on the order of, was it one solar mass?
Yeah, let's
right. And
right.
can you remind me of what that how that translates to in terms of delay? That's like microseconds, is that right?
I have another party trick for you. It's 20 microseconds per solar mass.
Right. By the way, remind me to never go to your parties. I'm teasing. Okay, so a lot of the action happens really at those quite small scales, and that's particularly strong because of the scattering. If there's a lot of scattering, right?
Yeah.
So if there was a way to kind of like a priori know like the distribution or the contribution of FRB sources that are scattered and like demonstrably not scattered, could you mix that into a constraint, to say that you have strong constraints for higher masses based on some presumed population of non-scattered sources?
Okay. So I think, hang on, let me clarify one thing. So what we've done to make this plot is we've taken the measured scattering from every FRB individually, and we've used the scattering time scale and an assumed geometry to calculate the size of the scattering disk. We don't assume anything about the scattering here because we use the measured data, and the one thing we do assume is like the geometry of the host. I'm not sure if that informs your question.
Yeah, it does actually. I didn't realize that. Okay, so it's a measured. Okay, yeah, thank you. Yeah, I guess I'm just trying to get at some of the question of potential improvements on the constraints if you kind of had some radio burst properties can tell you exactly what the environment's like potentially, and but you are sort of deriving that already, so that's great.
Yeah, I don't think we can do better than, because even if you knew that the scattering, knew something about the host environment, if there is scattering along the line of sight, it turns out that this in the geometry here, this is symmetric. So whether the scattering is coming from the host or something, or over on this side, it destroys your sensitivity either way. Now, what information that could be really helpful about the host environment is if you knew the host environment was really compact. If you can tell me that these FRBs have source environments which are 0.1 parsecs, then you could choose one of these four curves on the right here with some confidence. Here we've only chosen the 1 parsec curve because of the crowd pulsar is about a parsec in size, and that's where all the scattering is happening. But this is a choice. And if we have some handle on the host environment, we can turn that choice into a more motivated decision.
Okay, thank you. Maybe a quick follow-up question, just if there are no urgent ones, but you didn't talk about astrometric effects. Do you know if that's sort of in play with CHIME Outriggers?
Astrometric effects. So yeah, we're sort of in the process of studying our astrometric accuracy. Our precision is about 50 milliarcsecond per baseline. Our accuracy is on the order of 300. And the reason for that is some bugs in our clock pipeline, probably, which I am currently working out. And to test that, we've been localizing crab giant pulses, which we've observed with this ad hoc VLBI array.
Okay, cool, thanks.
Sterling?
Yeah, so I just wanted to understand the curves you're showing in the results are for the correlating the electric field. Presumably you have no problem measuring 100 or 10 to the 4 solar mass lens masses just by the old-fashioned way of looking for multiple bursts in intensity, right?
That's right. I think that the difficulty there then becomes a morphology game of trying to convince your referee that what you've seen is either a lens or not a lens. I'm looking at the chromaticity. Because you see all these FRBs, you look at them with high time resolution, as Dick will tell you, they have kind of funky morphologies, and it would be very difficult convince me personally that if you don't see an interference fringe, that it's really a micro lens, not just FRB sources doing weird things.
But then above 10 to the 10 solar masses, you can just localize.
Yeah. So I mean, one synergy which I didn't talk about is that if you do this microlensing search and you have localization capabilities, you think there's a source there, you can just localize it to like a giant lensing arc or something. That's a good point.
Yeah, I was just curious. You mentioned the limiting effects of things like diffractive scintillation or diffractive scintillation. Have you thought about how maybe like if you did have an FRB that was lensed by some sort of plasma refractively, like where you kind of entered into more of a strong scintillation regime past even just the pure diffraction. Would that how would that impact the coherence issue? Would that sort of would you still be facing sort of the decoherence that you lay out here, like limiting sort of the curve, depending on the nature of the scattering screen, or would that help you? Do you have like a
that's a good question. I haven't thought too much about refractive scintillation. I don't know exactly how that affects what we've been doing here. Mostly because my understanding is that in refractive scintillation, you're looking for motion to the screen.
Yes.
And the motion of the screen is pretty negligible over the duration of FRB.
Yeah, I guess depending on where the lens is located with respect to the FRB.
Totally.
Yeah,
Totally.
Yeah, that makes sense.
Dongza?
Very nice work, Kelvin. So a quick question is, like previously you said for the 2 FRBs detected at 2 sites, you fit for the geometric delay and the Earth rotation and the additional DM separately, and then how do you judge like how do you judge which is the value that you get, like with the like complication of the burst geometry or etc. Confuses you?
It actually doesn't, because yes, so there are these 2 contributions which both look like one over frequency. Sorry, I have a million slides. But one of the geometric contribution is actually mostly degenerate. Sorry, it's highly covariant with the black arrows, right? So you're asking about like, please correct me if I'm wrong, but you're asking whether the contribution from the ionosphere and the field rotation over the sweep are degenerate because they have the same frequency dependence.
No, more like when you do the fitting, how do you judge like what is the good fitting? Do you just try to align it, or you just try to maximize the signal in the correlation?
Yeah, so we have an estimator which I've written about. There's a likelihood you can write down as a function of position and marginalize over the spectral structure of the FRB. So you're independent of you're independent of your amplitude and bandpass in this way. And we're sort of learning that that might not be the greatest estimator, and looking at other ones is something that we're working on right now. Yeah, so we fit this model, and this model only predicts the phases. So you basically undo these phases and derotate everything and see how flat the fringe looks.
Okay, cool.
Yeah, I don't know if that helps. It's sort of hard to demonstrate this without a blackboard, but if you want to talk about this at some other point, we have to discuss.
Thanks.
And Calvin is around tomorrow, by the way, until.
Yeah, I am around tomorrow, although I do have some appointments with folks.
Any other questions? I have a question. Would you rather have, say, 100 FRBs localized to 50 milliarcseconds or 1,000 at arcsecond precision?
Probably the latter.
Yeah.
But that's because I'm personally interested in cosmology. If you are interested in host environments, then of course,
Yeah.
go for the 50 milliarcsecond.
Great.
That's a good question. Yeah.
Any final questions? If not, let's thank Calvin again.